Hello, this is Ken Stuzen. I'm a partner at Brown Advisory. Welcome to the Now Podcast. Now stands for navigating our world. Through these discussions, we try to understand the world better, to navigate some of the most pressing questions that are shaping our lives, our culture, and our investment challenges. The race for AI supremacy is significantly increasing electricity consumption. Hyperscalers such as Microsoft, Google, and Amazon are investing heavily in expanding their data center capacity, and this is straining the already outdated U.S. energy grid. As investors, we need to ask, is the current data center expansion exaggerated? What role will hyperscalers play in driving the energy transition? How will the energy mix change? And what role will nuclear energy play in this new paradigm? In this episode, which was recorded live at our Now conference in Austin, Texas, Brown Advisory's Catherine Kroll sat down with Dr. Brian Spears, Dr. Michael Weber, and Alex Hernandez, who represent leading-edge thinking across AI and nuclear physics, energy policy, and corporate reality to examine these questions and much more.
We're going to talk about the race for AI and what that means for national sovereignty, what it means for the energy transition, and what it means for the great state of Texas. My name is Catherine Kroll. I work on our research team, and this is a topic, even if I tried, I don't think I could stop hearing about. Already today, it's come up a bunch, and we can only expect this topic to accelerate. Recently, the conversation has felt really polarized, as has most discussions in the United States, so perhaps that's not unique. But my guess is that it feels polarized because it represents values that are being pinned against each other. This idea of national sovereignty, energy sovereignty, sustainability, low carbon solutions, can they all coexist? And the answer is, I don't know, which is why we have these three really smart humans with us to help us make sense of what we don't know and hopefully get a little closer to the truth. Now, you've probably taken a look at their bios in the pamphlet. I find them particularly dizzying, what these three have accomplished, but I'm going to give you a few highlights, all right? So I'll start with you, Brian. Dr. Brian Spears is the director of the AI Innovation Incubator at the Lawrence Livermore National Laboratory, which, for those of you who don't know, is charged with overseeing our country's nuclear stockpile and national security. Pretty high-risk stuff. Maybe not as high risk as having your parents in the audience, though, right? That's pretty big. Hi to Brian's parents. We also have two away, Dr. Michael Weber, who is the Sid Richardson Chair of Public Affairs and the John J. McKetta Centennial Energy Chair at the University of Texas at Austin. I went to UT, so I happen to know that Professor Weber is really referred to as the Matthew McConaughey of energy. So we're in good hands there too. And finally, we have Alex Hernandez, who is the CEO of one of the premier nuclear companies, Talon. It's been in the news. You've heard about it, which means you've heard about him. And today he's helping to pioneer hyperscalers, really make sense of the very dilemma that we'll get in today. So our very own corporate visionary. We're in really good hands. Before I get to them to help us unpack all of the unknown, all of the headlines, all of the fact versus fiction, let's set the stage with what we do know. It's a really short list, in my opinion, 4 things, okay? The first is that tech companies are big, really, really big. If NVIDIA was a GDP, it would be the 8th largest in the world. Only 7 countries that would be bigger than NVIDIA, right? So what companies like it does really matters. What are they doing? They're building AI. They're building it quickly, and they're putting tons of capital behind it. The 4 biggest tech companies spent $200 billion in just this year, with guidance that that will likely increase. Why does that matter? Point 3. AI is energy starved. It wants natural resources, and it could take up as much as 9% of our total electricity need by 2030. Maybe that sounds like a lot to you. Maybe it sounds like a little. But when you put it into the broader ecosystem of my fourth and final point, we are in an energy inflection tipping point. It really does matter. We had a Now panel about, I guess, how many years ago was our first Now panel, Tim? 16? 16 years ago. And our CEO, Mike, was telling me that at that time we had a conversation about the aging grid infrastructure. And Michael, you'll help us understand, has that changed? Hasn't it? The chances are we were really going to need to figure things out, and quickly. And that's probably why we've seen this huge renaissance of nuclear energy. Constellation Energy, which Christine mentioned in her final closing remarks, has been up 120%, all because of these ideas around AI and national security. So there's a lot going on. That's it. That's all I know. I know that the companies are big, that they want AI, that they use a lot of energy, and that things are changing in our energy system. So with that, let's get into some of the headline and what we don't know. And I think we just have to start with, like, what is this AI thing anyway? Is it overblown? Is it hysteria? And what should we do about it? And I'm looking at you. You gotta take the first one, Brian. What do you think?
All right, I'll take a stab. I'll start with a controversial position. AI is actually underhyped.
Okay.
So you might think, how can that possibly be? It turns out that it's really well hyped for the things that we use it for every day, for writing, for generating performance appraisals, for finding efficiencies in human resources systems. We can sort of grok that. But AI today can help us discover new materials, design new systems, from weapon systems to technology systems, automate manufacturing, close that entire loop in an autonomous system, and it does that in a way that we've never before seen. There's a problem. It's not hyped enough because the specialties in some of these models provided by the hyperscalers, like the OpenAIs and the Anthropics of the world, are getting to have capabilities at the PhD level that only a few thousand people on the planet can truly appreciate the impact of. So I have led a team in modeling and simulation to bring inertial confinement fusion to humanity for the first time in history, which is a great thing to be able to say.
Will you say it again? Because that's a lot.
I led a team to bring fusion gain, we call it, to get more energy out of a fusion capsule of fuel, get more energy out than what we put in with the laser system that we drove. So that's been a goal for humanity since the laser was invented. So we worked on it as part of the US government for 60 years. We used AI as part of our quest to be able to do that. So we failed for a very long time until we succeeded. The point is, AI systems can be used by folks like me and my team, and it's very hard for other people to understand what those tools and capabilities can actually do unless you have very specialized, very deep and niche knowledge. So there's a sense that this is underhyped because it's transformative. There's another angle in which it's transformative that comes back to the energy usage. What I'm really saying to you is that if you look at what GPUs do, graphics processing units, on driving AI systems, they are effectively now capable of turning about $100 worth of electricity into a year's worth of human cognitive labor. So at the Industrial Revolution, we took energy and turned it into mechanical power, cranes, steam engines, things like that. We're now taking energy and turning it into cognitive labor. This is not the creative thought or the executive planning that we all pride ourselves on being able to do, but this is cognitive labor where you turn power into the output of a year worth of human brain power. And the capability to then scale that to the PhD level is transformational. And the last point I'll make in this sort of opening piece is that the United States is not the only country that has noticed this. So we are clearly in a global race with our only adversary on the planet who can compete with us, which is China. They've said very clearly that they will dominate the United States in AI by 2030, and we don't have much of a gap. So between the leaders in the AI industry in the US commercial sector, like OpenAI, and maybe some of the laggards who are further behind but are still quite capable, we might say there's a 6-month gap in capability. Maybe it's slightly larger. There might be the same size gap between those laggards and the state of the art in the Chinese capability. So we don't know it exactly, but let's call it 12 months. That 12-month gap of turning energy into cognitive labor is something we have to seize for US advantage today. Every month that we do not do that, we cede some of that strategic advantage for national security. And we talk about all the ways that we can either seize that or we can let it go. But it puts everything very clearly. Robin mentioned earlier that we face the idea of a new Cold War, and I think that's not very far from wrong. It's just not a nuclear Cold War only. It's an integrated deterrence war, and one of the fronts will be the quest for AI dominance.
So a 12-month head start is what we have right now.
A 12-month head start. And that's a 12-month head start in building out AI capability. What we need to do to seize AI and do something with it is turn it to advantage on manufacturing systems, on defense systems, on things that move mass and energy in the real world. Yeah. So every moment that we don't do that in our system, where we have a strict division between what we do in the private sector and what we do in the public sector, we lose ground to a China that's organized to intentionally and strategically blur those lines. So a 12-month advantage for the United States could go away if it's adopted and used for, say, national security purposes to accelerate the Chinese nuclear stockpile, which is something that I care greatly about. We have a new tripolar world where our only peer adversaries in nuclear deterrence are Russia and China. China is the only one who can pair that with an AI capability and do something on a pace that could outrun the United States. And all of these things together face the energy transition you're talking about. I will agree with Sam Altman in one statement, that is, infrastructure is destiny in AI. So yeah. China is building gigawatt data centers in the Gobi Desert. You'll have lots to say about what it looks like. And the United States has got to compete in order to make sure that we don't see it our advantage, in fact, that we pull further ahead.
Alex, I want to turn it to you and translate this into maybe something that feels a little more tangible for those of us that don't share your educational background. When we look at the likelihood of the data centers being built out, we know a lot of money is going behind it. I read sell-side reports that sometimes say, this might not happen. And then you and I were just discussing what was in the news relating to Talon and FERC, which you'll summarize far better than I will. But tell me where your head's at with the likelihood of, and maybe call it the optimism of these data centers being all that we can really expect from tech companies in the next few years.
Yes, well, thank you. Thank you for the question. Thank you for hosting us, and delighted to be with all of you today. We should have organized this in order of IQ with me sitting at the end.
No.
Because I'm neither a doctor nor Matthew McConaughey. So I'll apologize for that in advance. Look, I would start with the theme, Brian, you mentioned, which is that I do believe that infrastructure is, in fact, manifest destiny in digital infrastructure in AI. There's an important element around technology that Brian and others are working on, Jensen and NVIDIA, but all of this innovation does not occur with the right infrastructure in place to enable it. And that infrastructure is, it's energy infrastructure, it's data center infrastructure. And to zoom out a little bit, there's a rapid collision, convergence happening in the world between the world of energy and the world of data and AI, because in effect, computing is an energy business, and the energy business is now becoming a computing business. And how you connect those two things, I think, is one of the most important generational infrastructure questions that we have to answer. How we do that, I think, in an innovative way, and we'll talk about cumulus data in a moment, I think will present, a generational investment opportunity for years to come. And it'll also be the key factor that determines the dominant, hegemon across the world around AI technology and innovation. The way we approach that problem at Talon and Cumulus, and I left and retired after the sale of the business to Amazon last year, was that we saw that currently data centers were being provided and supplied by what were monopolies across the United States. Those monopolies are called regulated utilities, and they set up to effectively bring power to your home. They weren't designed to power massive campuses in metropolitan areas that consumed volumes of power at a scale that was never conceived when the electric grid was constructed in the US. And our simple observation and thesis in creating Cumulus Data was that if we could create a data center business, an infrastructure business that would supply AI, supply the cloud, but do so by connecting that data center, that AI, directly to power, without the utility monopoly as the intermediary, that if we could do that, we had something that had a competitive advantage in unit economics, in scale, in time, and particularly in co-location next to one of the safest and most important assets in our domestic infrastructure, which is nuclear power. And that ultimately led to the creation of Cumulus, which is now, we sold to Amazon Web Services in March 2024. Amazon will now invest $12 billion into that campus over the coming years to construct 17 buildings. It'll be one of their largest data center campuses in the globe. And in my opinion, we were the first, but this is not the first to occur. It's the first of many, in my opinion. The incumbents will be vehemently against it. The monopolies and the current intermediaries will be vehemently against it. But those who innovate ultimately will win. And I think there's very few things in our national agenda that rank to this level of importance of setting that infrastructure in the right manner to win this race, which is, in my opinion, national security imperative.
It's an incredibly useful lay of the land, and I want to come back to a lot of it. I want to start, though, with two words you said, nuclear and safe, and you use them in the same sentence. And I want folks to just take a pulse check of where that lands with you. You hear nuclear energy, do you think safe? Data says more and more people are, but Michael, I want to hear from you. When you think about the challenge of our aging grid, I keep going back to a comment you made a few weeks ago that, and you'll do it better than I will, in the next 20 years, we need the same amount of energy as we've put on in the last 100 years. How do we get there? And obviously, we'll have to have new, or perhaps not obviously, my assumption is that we have to get comfortable with things that were off the table before.
Yeah, exactly. So we're going through this growth phase, which we haven't had for a long time. We've had about 100 years of growth in the power sector. Mm-hmm. In the last 20 years, we're flat, and now it's about to grow again. And we've lost our muscle memory on how to grow and how to build quickly, how to get permits, how to get siting, how to get regulatory approval, how to put it in the rate base or not, or whatever. It's like all of that we have to get into growth mode. And at the same time we're growing, we're also shutting down some older, dirtier plants because we've had different waves of build out, late 1800s, and then the first citywide networks in the early 1900s, and rural electrification in the 30s and 60s, and then another wave, 70s, 80s, and the gas build out in the 90s and early 2000s, and now another build out. So we have these different waves. We have a lot of old coal plants that were built in the 70s that are ready for retirement. So we have to replace the coal plants and also double. So it's a compounded problem. Yeah. And we need to do that with transmission lines that were mostly built 30 to 40 years ago, some 100 years ago. So we have to expand the grid. And we're talking about doubling or tripling. We might double it in gigawatts and triple it in gigawatt hours. So we might double the power and triple the energy consumption for data centers, electric vehicles, heat pumps, factories, you name it. And that's hard to do. So we have to do it. And if you're in a growth mode, you have to use everything, although maybe we wouldn't use coal because it's just too expensive to make coal clean. So you talk about nuclear and geothermal, wind and solar and batteries and hydro or hydroelectric dams where you can build it, which there aren't that many sites left in the United States. So nuclear's on the table, and I think that's pretty exciting, frankly. And yes, who thinks that nuclear is safe? Like, I'm an engineer. Most engineers think of nuclear as safe. Most lawyers don't. Most lawyers think of nuclear as a liability waiting to happen, right? So we are maybe at a mode where we think, well, the risks of nuclear are worth it because it avoids some other risks around climate change or the risk of not having enough power. And so nuclear is back on the table along with all these other options. And within nuclear, there's fission and fusion, as you heard. So I think it's a pretty exciting time to be in the power sector. And I have students now, I've got all these students at the University of Texas who are starting to say they want to go to an exciting, innovative career in the utility sector, which is not what people would have said 15 years ago, right? So it is just like the world has changed in terms of the cultural acceptance of nuclear. That's like in the last 6 months, but also student interest in the power sector in general. So a lot of growth, we got to get ready, which means every tool in the toolbox, frankly.
Can you bring that to Texas when you think about the growth that we need? I think many of us in this room have lived through what happens when an extreme weather event occurs. I mean, really bring to our lived experience, the energy challenge, and then we'll get into the opportunity that's ahead of us.
Yeah, absolutely. So Texas is sort of a preview of the future because we're expanding, we're electrifying, we're decarbonizing, and operating in a warmer world. We're doing all of it at once. And so Texas is a preview of this. And There are a couple different things happening at once. One is we've had a lot of growth in the last year since that Winter Storm Uri in February 2021, and I lost power. It feels like we all lost power for days on end. 14 million people didn't have water. It was a massive problem. Hundreds of people died. $100 billion or so of damage and economic losses. So it was a pretty big event. I can't believe we're coming up on the 4th anniversary of that in just a few months. Since that time, the demand has grown from 70-something gigawatts, about 74 gigawatts, to over 85 gigawatts. We added more demand for the grid in the 2 years right after Uri than the prior 15 years. So the rate of growth is very different. And there are a couple of different things happening. One is the Russian invasion of Ukraine changed global prices for energy commodities. We have a lot of electrified liquefaction of gas to send to Europe and other places. Electric vehicles, heat pumps, other things. Electrified oil and gas. Oil and gas pumps and extraction systems can be electric because it's cleaner and cheaper, but also data centers is a big part of that. Around the same time, China kicked out the crypto miners and they moved to Texas. So about 5 gigawatts of that is data centers. So we're seeing the growth and we're seeing the strain that comes with that. Now we're also building wind and solar and battery. We're trying to build things to keep up with it. And the governor's really pushing for more nuclear as well. But Texas is that preview of what happens when you have growth that creeps up and then turns steeply. How do you build quickly enough and operate in a warmer world and keep the grid from collapsing? Well, it's not impossible, but it is hard and you have to be intentional about it. But I think that's going to happen kind of everywhere.
Yeah, it's well put. It gives me a sense of where we've been, where we are right now, and I think we can transition to where we're going when we think about energy systems and especially nuclear. When we were catching up a week ago, I made a very bad joke that I had heard in my defense from your boss, which was that fusion is the forever 30-year away solution.
Right.
Tell me why that's a really bad joke.
Yeah, I mean, the traditional telling of the joke is fusion power is 30 years away and always will be, right? So that joke has been moved and changed to, well, a fusion demonstration power plant is 30 years away and always will be. And then for me specifically, we tried to ignite a fusion pellet in our laboratory with a $4 billion laser that's the size of a football stadium. And the joke was, your ignition event is 30 years away and always will be. But that happened. It's in the rearview mirror. So it's a bad joke in the sense that with will and determination, the United States can do things. The laser was invented in 1960. Someone had the idea at our laboratory that you could probably squeeze nuclear fuel hard enough that you get more energy out than you put in with a laser. And then we focused on it for 60 years, doing hard things, and made it happen. So that joke that fusion is 30 years away and always will be is both a bad one and it's also a model. The United States should pick up those hard things and invest in it with national will to go do it. Yeah. And that's public funding, but it's also from people gathered here today. There are tremendous opportunities for both individual private things to happen and public-private partnerships to drive this forward. So that should be a motivator for those of us who are thinking about how to change the world. These difficult lifts we can do. It just takes creative thinking. And for a room like this, it's not just the scientists and the nerds like me thinking about the technology, but we need creative capital stacks behind it to go move quickly. I am constantly talking to our US government to try to fund an AI ecosystem for doing these kinds of things for national security, and that is a 2-year at best, 7-year at worst, or forever kind of conversation. We need the kind of reaction time that can help us be quick for fusion power, for responding to the data demands that we heard. AI, the half-life for AI to change, or the characteristic time that it gets really excitingly different, is about 6 months. So we now need solutions like new fusion power solutions. Maybe start with fission, small modular reactors or something like that. Work your way up to fusion and then have a long sustainable future. You don't have to give up on the sustainability. You have to go out and do something about the situation. So.
And going back to your timeline example of the US edge we have 12 months, apply that same timeline to the success we've had in getting closer to fusion. How much closer are we than we were 30 years ago?
Yeah, we'll see the joke, right? We're far closer. So there are 2 ways to squeeze things and get fusion energy out of them. One is by magnetic confinement, things that are called tokamaks, these donut-shaped things that squeeze the fuel. Those are very well-engineered devices that can contain the physics The physics demonstration is yet to be done. So there's a risk that needs to be borne by somebody in the public or the private sector. On the inertial side, the government has de-risked the physics. We've shown with a laser driver that it actually works at terrestrial scale, and we can see it and we can do it repeatedly. The thing that is off in the distance is the engineering capability to do that. So I mentioned that my team and our laboratory did this for the first time in history and 6 subsequent times or so. But to be economically viable, it has to happen at 10 times per second. So it has to happen almost as fast as incandescent lights flicker, which you can hardly perceive. That's a huge engineering risk that someone has to solve. So we are very, very much closer because we know it is physically possible. It is, and the mechanical engineer in me hates to hear this, just engineering to go from that physical demonstration.
We're nice people. We're helpful. We'll do what we can. It's a good. Yeah.
He's the chair of the department I got my degree in, so I can say that. But we are far closer, and I'll come back to that notion of will. It really is just the private sector understanding how to work with the public to buy down some of their risks, extract value from it, and go seize the science, tackle the engineering, and make it work. There needs to be a demand signal, and I think in this conversation, the demand signal is there. We're having AI companies that are asking for gigawatt data centers. So what does a gigawatt feel like? At our laboratory, we have about 100 megawatts of power. That is the most capable high-precision machine room on the planet and would power a small city. It's enough power to push a submarine through the ocean for the military. And then we have AI providers who want 10 times that. So 10 subs or 10 cities just to do compute. So that's the demand signal that's going to take the technological capabilities that have brought that somewhat closer and then bring it far closer because there's motivation to go do that.
You mentioned SMRs. Alex, I've read a lot about them as of late. Imagine my surprise when I learned we don't actually have them here yet.
Yep.
Is this another area of over-optimism, or how do you think about the future of this next step in, as Brian laid it out?
Yes, it's going to be an important part of the solution, but not an immediate one.
And maybe talk a little bit about what they are and why they're important.
An SMR is a small modular reactor. It's a plant that could live in a submarine, but could be put adjacent to a city, adjacent to a data center, and in a very efficient footprint with no carbon, effectively power this AI race. The reality with SMRs is, notwithstanding the best efforts of innovation in America, they're unlikely to be fit for purpose over the next 5 to 10 years. And there's going to need to be a transition, right? And so maybe zooming out to Brian's comment, we have to have the right dream of leading this technology. It's a national security imperative. It's an imperative for our economy. We have to plan accordingly through policy and through investment. And then we have to execute relentlessly with the best innovators in the country and the best business people in the country to get there in that sequence. And people often forget, before I go back to SMRs, that today we have 100, roughly, operating nuclear power plants in the United States. They're operated by my former company, Talent Energy, and Mac McFarland, the CEO, or Joe Dominguez at Constellation, who owns the majority of plants in the United States. And so there are many existing nuclear power plants in the United States. They provide roughly 25% of the power in the country on a carbon-free, reliable, and safe basis, right? And many people don't know that fact. It's really, really important, right? So we start with what we have. Natural gas, just being here in the state of Texas, which is abundant. There's virtually nowhere in the world where this is more abundant than in our state, will increasingly play an absolutely critical role both for the existing generation fleet in Texas, as well as for all of this incremental generation that needs to be constructed to satisfy both population, economic, and data center growth. Natural gas will absolutely be a bridge complemented by renewables in our state. And then I go back to SMRs. I think SMRs will ultimately be there, but they will ultimately be there, in my opinion, in 1 decade. And how we transition through that solution thoughtfully and with purpose and by planning and with investment is something that's difficult to do in the policy arena, but it's an absolute imperative for it to happen, because we need to reimagine a place in the United States where our infrastructure is located in these gigawatt scale campuses I believe they'll be adjacent to where there's energy abundance, whether that's adjacent to nuclear power, adjacent to natural gas. Many times they'll be in places in America that have been forgotten by the world. They will not be in Virginia. They will not be in New York City. They will not be in San Francisco, right? They'll be in West Texas. They'll be in Pennsylvania. They'll be in Ohio, in North Dakota, in Montana, in places that are going to experience a revival of employment and of innovation in America because there is energy abundance, because they want these investments, because we have the fiber infrastructure to transport this energy and information to where the energy and information need to go. And transporting information is a much more efficient way than transporting electricity via electric networks. So we need to re-envision the way that the US is going to look in 5 and 10 years. And in my opinion, we're at an inflection point in time that is as significant as the construction of the railroads in the United States, as significant as FDR's construction of the highway system in the United States, as significant as the movement of power from New York City to Niagara. And the faster we realize that and align, both in business and in policy around that objective, the better the economy of the US will be, the better our national security will be, and will ultimately be, as we have been, the leader in these areas. And to the extent we don't, our adversaries, I can assure you, will get there faster.
I think that's a really important perspective for a lot of reasons, not least of all your commentary around decarbonization and the choices we'll have to make. Michael, when we caught up a few weeks ago, you had said that in the next, I think it was 20 years, that you anticipated the world changing 2 times over. And you just look back at what we've experienced in, heck, not even the last 20 years, less than that, but whether it be geopolitical conflict, a pandemic, you name it, something's bound to happen. And those are scary things, but there's also the potential for something perhaps more optimistic to happen as well. So I think, there's the grounded reality of where we are today. When you dream big, what could it look like?
I mean, the exciting news is that the energy system will probably expand energy services and clean up at the same time. And so that's a pretty exciting transition. And I would argue we're 5 to 15 years into a 30 to 40 year transition in the United States. Like, we already started our transition. Maybe our CO2 emissions peaked like in 2006 or something. So our emissions are dropping. Our energy consumption's level, despite increasing population and economy because of efficiency. And that story that's happening in the United States and the UK and a few other places will happen around the world. So that's pretty exciting that we will improve the access to energy services by people, but in a way that's cleaner, more reliable, cheaper, this kind of thing. This is a good news story. There will be some hiccups. You said, like, some of the solutions might not be available for 8 years. We still need power here and there. I don't mind the SMRs might not be here for a while because we'll need power then, and I don't mind the fusion might not be here for 15 or 20 years. We'll need power then as well. So we need all the solutions, including the current ones. But what we haven't said is on the electrification side, as we electrify data centers or electrify factories or electrify oil and gas or electrify vehicles, we will use, yes, less energy in other parts of the ledger. So the total energy consumption actually might drop because with the efficiency of the electric drivetrains, you reduce your overall energy consumption despite being happier, more productive, and safer and everything else. So there's a lot of good news there. There's also a lot of scary things. We might shift who we depend on for critical minerals. We used to depend on one region of the world for strategic liquids, and now we might depend on another part of the world for strategic minerals. We might change some of the supply chains in ways that we aren't used to. We might need to relearn how to open mines in the North American continent. There are a lot of things we'll have to learn in the hiccups that will happen, but I'm pretty optimistic, frankly, about the energy story. Now, there are other reasons to be nervous about geopolitical shifts and fall of democracy or other things around the world, but I think the energy story is actually looking pretty good. And the fusion and fission and data centers creating the large demand to bring these solutions to the market is pretty interesting. Now, we just have to make sure we do it the right way and don't build stupid stuff that we're stuck with for 60 years, which is what we did in the 70s and 80s. So we are known to build stupid stuff and then be stuck with it, so it'd be better to build the smart stuff. But that infrastructure, that mindset we must build to enable the future is key. You mentioned railroads. I think in 1860, Abraham Lincoln ran on a platform, a pro-canal platform. We're going to build canals, the critical infrastructure for American trade and national security. And so it was canals, it was railroads, and then it was rural electrification, it was highways with Eisenhower in the 50s, rural broadband in the early 2000s with Bush, and now we're talking about expanding the power system. So it's a part of the American story is just the flavor of the infrastructure changes bit by bit. And frankly, I'm pretty optimistic. And I would say that workforce is the thing I worry about the most, frankly. And I train thousands of students in person, online, professional learners, you name it. We cannot get people through the system fast enough. It includes the PhD grid modelers. We need like 1,000 grid modelers. What a niche thing, but we need 1,000 grid modelers to do the project planning and do the permits. We need 100,000 electricians. We need a couple 100,000 pipe fitters. We need hundreds of thousands. There's just a missing millions kind of employment gap. And we have millions of missing people between the deaths of COVID and the change in immigration policies the last 8 years. There's 1 million fewer immigrants, and I think it's about to become even more stark. So this is a huge problem. The thing I think we'll trip over the most is workforce. AI and autonomy might be the solution. It's probably the only solution we got, frankly. There just aren't enough people to do the tasks we got.
I think it feels right to end this on the note of people. Ultimately, AI, energy transition, national sovereignty, it all comes back to people and how we can make this work. So thank you for your incredibly thoughtful comments, the work that you do, and for being here with us today.
Thank you.
Thank you.
Hello, this is Ken Stuzen. Thank you for joining us as we seek out insights that help us better understand our rapidly changing world. We hope you'll tune in for our next Now episode. Until then, be well and stay safe.